the last day of school that Tuesday, do we have your class?
Yes, yes, you will. But we're gonna like play a game and just relax and have fun.
So is there only 3 sections?
Yes, there's only 3 sections. Okay, so this is 14.3. It says the normal distribution is one of the most important distributions in statistics since it is found to be a suitable model to represent many naturally occurring random variables which are distributed in this way. Such variables include the physical attributes of people, animals, and plants, and even the specifications of mass-produced items from factories. The distribution could also be applied as an approximation of, for example, student exam scores, time to complete a piece of work, reaction times, or IQ scores. So you may have heard this called the bell curve. Have you ever heard of the bell curve? Okay, so if you look to the right, there's the bell curve, but it's called a normal distribution curve. Yeah. Oh, thank you. So what I want you to notice is mu. Mu is the mean, and sigma is the standard deviation. And we're going to go over this in just a moment, but I wanted you to understand this normal distribution curve. So mu is in the middle. So that's that vertical bar in the middle. And there's symmetry, okay, this is symmetrical, but what we have is 68.26% of the data lies within one standard deviation of the mean. So if you notice, it's 34.13% within one standard deviation to the right, and it's 34.13% within one standard deviation to the left. So total, it's 68.26. It's within one standard deviation left or right, okay? Then 95.44% of the data lies within 2 standard deviations of the mean, and 99.74% of the data lies within 3 standard deviations of the mean. So do you notice that that is a teeny tiny part that's not within 3 standard deviations of the mean? All right, so the characteristics of any normal distribution. There is no single normal curve, but we have a family of curves. Each normal curve is defined by its mean, mu, and its standard deviation, sigma. Recall that the mean, mu, is the average of the data. And the standard deviation, sigma, is the measure of the data's spread. Mu and sigma are called the parameters of the distribution. And we can write x, and that's a little tilde n, of mu, comma, and it's sigma squared. Well, what is sigma squared? Variance, okay? That's actually the variance. To say that the random variable x is normally distributed with a mean of mu and standard deviation, sigma. Note that in this expression, it's actually the variance that's written as the square of the standard deviation. In any normal distribution, no matter what the values of mu and sigma are, now here's our connection. You may be like, what on earth does this have to do with anything we've done in the course? Okay, in any normal distribution, the total area under the curve is always equal to 1. What math concept did we do that was area under a curve? Integrals, okay? There's the punchline, there's the connection, okay? We can therefore consider partial areas under the curve as representing probabilities, okay? So let me go back and reread this again. In any normal distribution, no matter what the values of mu and sigma are, the total area under the curve equals 1. So we can make a connection to probabilities because probabilities have a sum up to 1, right? Okay, cool. Unfortunately, the probability function that's equal to this normal curve is very complicated, and it's right here, okay? It's nasty. Do you see how horrible that looks? So it would be very difficult for us to use integration to find area under the curve, and hence find the probabilities. However, there's an easier way to do this, so I'm going to show you that. So what we can do is, like, let me give you an example. Say in manufacturing, they're manufacturing something where they want the average, the mean to be 500 grams, and one standard deviation is 3 grams. So I'd have 500 in the middle, I'd have 497, 503. And then if I want 2 standard deviations, that'd be 594, 506. So your numbers on the x-axis are going to change based on every situation. So what we do, though, is you can do something called a standard normal distribution, where mu is 0 and sigma is 1. Mathematicians always use capital Z to describe a random variable with a standard normal distribution. And we write that Z is normally distributed to N with a mean of 0 and a standard deviation of 1. We can use our graphing calculator to calculate the areas under the standard normal distribution curve for values of Z between Z equals A and Z equals B. This allows us to calculate then the probability of Z between A and B. So in example 1, it says sketch the required area under the standard normal curve, then find the probability using your graphing calculator. All right, so what we're going to do is, since this is a standard, this tells you it's a standard normal curve, which means the mean is 0 and you have a standard deviation of 1. Now, I'm not looking for perfection because, as you can tell with mine, I'm not too swift with this myself. And in part A, we want to find the probability where Z is between -2 and 1. So I am looking, that probability is equal to the area under this curve. So guess what? On your graphing calculators, get to a blank doc, you're going to type menu 5, 5. Let me pull mine up. And what we're looking for, I think I plugged my calculator. Yeah. All right. All right, so you're on just a calculator page. So you do menu, 5 is probability, 5 is distribution. And now we are going to use here number 2, that is normal CDF, because it is a range. So then you're going to put in -2, 1, and then now this will be able to change, but for now it is a standard normal distribution. So the mean is 0, and the mean is 0 and the standard deviation is 1. So what is in here is your minimum, maximum, mu, and sigma. So what you're putting in this parenthesis for normal CDF is minimum, maximum, mu, and sigma. If it's a standard normal curve, and do you notice it's automatically 0, 1? On mine, I want you to notice that the lower bound, like if for some reason you had something like x less than 2. In mine, it does -9e9999. That's just saying it's going to negative infinity. So you just like leave that one in there if, and we're going to see that in part B. I'll show you that in a moment. But I'm going to change it. I'm going to put -2, 1. The other numbers are fine. And are you getting that the probability is 0.819? Yeah, okay. All right, letter B. So if you want to do a normal curve, you're always going to go 0 and -3 to 3. And if I want z, the probability z is less than 1, so this is going to go normal CDF. Now it's going to negative infinity. When it goes to negative infinity, you're going to leave just this random small number in here, the -9e999, and it'll go 1, 0, 1. But what I want to connect here is that the probability, because we are changing this to a standard normal distribution, what it's saying is this total area under this normal curve is 1. So it is equivalent to doing probability. So the probability of z less than 1, what that's doing, because I don't want us to, we don't have to shade anymore because I think you get the gist of it, right? Is that then that area under the curve represents the probability. So then I got 0.841. Okay? All right, so then in this one, when you go to do this one, you're going to do normal CDF. I have -1.5, but then greater than. Well, what you're going to do is you're going to just type in a bunch of 9s. It doesn't matter how many. Because do you understand that what we talked about above is that once you get past 3 standard deviations, that is such a teeny tiny percent that it's really going to be like, doesn't matter. So that's going to be 0.933. All right, try D, and then I want you to hold off on E, because I'm going to need to refresh your memory on absolute value inequalities. So I would like you to write out like what you're going to type in the calculator. That will help me to know what you know. So I have normal CDF. So I'm going to leave that number in. It's 0, 0, 1. And what did your calculator give you? It gave you 0.5. Now, why do you think it did? Think about what probability I'm looking for. And just look at one that we've drawn up here. It's exactly half of the bell curve, right? X is 0, that is the mean. That means half the data is to the left and half the data is to the right. Okay? So that makes perfect sense. All right, now let's look at letter E together. And this one, I don't know if you remember this. If you have the absolute value of x is greater than a, you did this back in algebra 2. Because this is going to appear in homeworks. The absolute value of x greater than a, and let me do a little example underneath it. So if I had the absolute value of x is greater than 3, that would mean x is greater than 3 or x is less than negative 3. Does that make sense? Because like if I had negative 4, absolute value negative 4 is 4, that is bigger, okay? So having said that, I need to rewrite this then as the probability of z greater than 0.8 and the probability of z less than negative 0.8. So you're going to need to do both of those and add them together. Now, before you do that, let me make your life a little bit easier. Do you understand that because of the symmetry, couldn't I just find one of them and double it? Oh, okay. You know, I mean, instead of doing this work twice, there's symmetry. So the probability of z greater than 0.8 is actually the same as the probability of z less than negative 0.8. So just do one and then double it. So you're just going to put a bunch of 9s in there and multiply that by 2. Are you getting about 0.424? Yay, good job, good job. All right, so let's pause here and just make sure we're like just conceptually understanding what's happening here. Is a normal distribution curve is the bell curve, okay? That is the bell curve. The mean is in the middle, and you have up to 3 standard deviations away, we'll have 99.744% of the data. You can change this to a standard normal distribution where you can convert the mean to 0 and the standard deviation to 1 because it's not always that. So many real life random variables which are normally distributed do not have a mean of 0 and a standard deviation of 1. It is possible, however, to transform any normally distributed variable x to make it normally distributed to mu and sigma squared. This is possible because all normal distribution curves have the same basic bell shape, and so can be obtained through translations and stretches. Therefore, we can actually do a conversion here and use this formula. The z equals x would be your given like data value minus mu divided by sigma. This process is called standardization. So look at example 2. It says x is normally distributed 10, 2 squared. So what I know is mu is 10 and sigma is 2 because they're giving me sigma squared. So if I want to find the probability of x is less than 13, I can standardize this so that it will have a standard normal with mu is, the mean is 0 and the standard deviation 1. So watch, I can take z, the x value is 13. So this is 1.5. So go ahead then and go to your calculator Now I've converted it so that the mean is 0 and the standard deviation is 1. So you're going to go to your 552 and do the normal CDF. So you're going to leave that lower bound of negative 9E999 in. Did you guys get 0.933? Yay, good. Okay, in part B, find Z. See if you can find Z. Did you get negative 0.5? So this is going to be the probability of Z greater than negative 0.5. And you get 0.691. You guys got that okay? All right, now in letter C, if I want the probability of X between 9.1 and 10.3, then what I have to do is I have to convert both numbers. I actually have to convert both numbers. So I'm going to do Z is 9.1 minus 10 over 2. And Z is 10.3 minus 10 over 2. Yeah. And did you get 0.233? Did we get there? So right now, what we've been doing is we've just worked on mechanics. Okay, we've just not worked on mechanics. And the nice thing about this topic is there are so many real world examples. Like you actually use this in the real world. Industrial engineers would use this. Most engineers would use this. In business, they would use this. There's a lot. So let's look at example 3 and see if we can't look at an actual application. It says eggs laid by a chicken are known to have masses which are normally distributed with 55 gram, mean of 55 grams and standard deviation 2.5 grams. Find the probability that a single egg laid by this chicken has the following masses. So what I wanted us to do first is I wanted us to draw a normal distribution curve. So the mean is 55. And we're going to do up to 3 standard deviations away. So that would be what? 57.5, 60, 62.5. Let's go to the left. That's 52.5, 50, and 47.5. All right, so in part A, I want to find the probability that the mass is greater than 59. So you're going to do a normal CDF. So I have 59, comma, I put a whole bunch of nines in. The mean is 55 and the standard deviation is 2.5. So pop that into your calculator. And are you getting 0.055? Now I want you to stop and think about this, okay? So I want you to I want to conceptually understand what's happening here. Do you see 59 is about here on the normal distribution curve? It's saying that that's 5.5% that a single egg laid by this chicken has a mass of greater than 59 grams. And that should make sense, right? Because that's in a teeny tiny area. Okay, that's what's happening here. All right, go ahead and try B and C. Write the probability statement and then compute it. All right, for part B, did you get 0.212? Awesome. All right, keep going. For C, did you get 0.230? Yeah, okay, good. All right, and did you notice that we didn't have to standardize it? And technically, in example 2, I didn't have to standardize that. I could have entered that the mean was 10 and the standard deviation was 2. However, I was leading you to another part. Like I just needed you to know that skill because then we're going to use it here. What if I don't know the lowercase z value, but I know the probability that I want? Well, there is something called the inverse normal distribution. So here's an example. Suppose the owner of a company that fills cartons of juice to a mean volume of 150 milliliters may wish to find the volume below which 5% of the cartons are in order to reject them. The calculator has an inverse normal function which will do this. We will look first at inverse normal calculations using the standard normal distribution, where z is normally distributed to a mean of 0 and a standard deviation of 1. If it's not, we're going to have to standardize it because the calculator only does the standard normal for inverse. Okay, so that's kind of something that's unique about the inverse standard or inverse normal distribution. And the other thing about the calculator, there's 2 things. It has to have mu is 0 and sigma 1, and the calculator only does probability of capital Z less than little z. So whenever you get greater than, we're gonna have to do a conversion. Okay, so there's the two key pieces. All right, so if you look at example 4, it says I'm given z is normally distributed with a mean of 0 and a standard deviation of 1. So if I want to find the a value when the probability of z is less than a equals 0.877, I'm trying to find the a value for which the area under the curve to the left of a is 0.877. Okay? So let me kind of draw. So this is 0. And I'm like trying to find some a value that the area under the curve is 0.877. How did I know that a was to the right of 0 when I made this sketch? Like, I don't know exactly where it is, but I at least know it's to the right of 0. How do I know that? And this circles back to one of those we talked about. How did you know? Yes, okay, do you see that? If it's more than half, it's to the right of 0. And if it had been like 0.3, it would have been to the left. It's not quite half of the bell curve. Okay, so here's what you're gonna do on the calculator. You're gonna press the 5, 5, and then it's number 3. It's inverse normal. And inverse normal needs the probability or the area under the curve, and then it's 0, 1. And it'll always be 0, 1. And are you getting A is 1.16? Okay. So now for part B, the calculator cannot compute Z is greater than A. Okay, it just does not. So what we're going to do is if I have, and this is mu is 0, if it's 0.2, I know A is over here, right? So what would be an equivalent? This would be, what would give me the same answer? This would be Z less than what? .8, good job. So if Z is greater than A is 0.2, that's going to be the same thing as Z less than A is 0.8. So go ahead and do your inverse normal on that. And that's 0.842. So again, the calculator only does capital Z less than lowercase z. It will not do greater than. So I'm going to have to change letter C. And then guess what? It's just 1 minus the A value. Okay, that's the quick way. So this will be, I want to find on the calculator the probability of Z less than A equals 0.45. And are you getting negative 0.12? I can't read my writing. Is that 6 or 0? What is it? 6, okay. Okay, now for part D, this one's a little bit confusing, and I think once I explain it, you'll be like, oh yeah, now I can do that. Okay, so what I have here is that A, the probability between negative A and A is 0.42. So what I know is there is symmetry here, and this is 0.21 and 0.21. So wouldn't this be then the same thing as the probability of Z less than A is 0.71? Do you see why that might be? Because it's the 0.5, this part, 0.5 to the 0.21. So then you just do that one on your calculator. And it's 0.553. That one was a little tricky.
Could you explain where you got 0.71 again?
Yes, yeah, so what I know is that the probability of Z that's between negative A and A is 0.42, okay? So, but my calculator will only do probability of Z less than A. So if I get, so this is gonna, so what it's telling me is the A value. So like, I wanna know where is this A value? So 0 to the left of 0 is 0.5, and then I know that's 0.21. So that's the 0.71. Because what I'm trying to find is A. I'm trying to find where is A on that x-axis. So I'm not trying to find like all of this. I'm trying to find where is this. And this is 0.5 and that's 0.21. Okay? And so what the inverse normal on the graphing calculator does is it tells me the location of A on that x-axis. That's what it's telling me. All right, let's go ahead. Actually, I think this is a good place to stop because I feel like our brains are kind of full here. And what I want us to do next is the group